All right, so I want to do a couple videos explaining kinematics in the context of doing derivatives. And the whole idea here is just that when we're talking about kinematics is just when you are studying motion. Kinematics, that's terrible handwriting. Kinematics is just the study of motion. And so when we're looking at a motion equation, we have usually a function of time that tells you the position. So this is where you are at a certain time. And if you take the derivative of the position, then you get the velocity. And then if you take the second derivative of the position, you get the acceleration. Okay. Now, the important thing to think about is what different quantities mean here. So, position could be either positive or negative or zero. And so that implies that there's some sort of a direction here. So, your position is either you are like ahead of an object, behind an object, or you're directly at an object. You can think of it as if you're running a race, your position could be how far ahead you go. That'd be a positive position. For some reason, if you went backwards, that'd be a negative position. If you're at the starting line, that'd be zero. Or you think about it like jumping. Positive means you're above the ground, zero means you're on the ground, negative means you're under the ground. Velocity is very similar to speed, but it also has a direction to it. So if your position is increasing, you have a positive velocity. If your position is decreasing, you have a negative velocity. And so that would mean, like, if you are moving forward, your velocity is positive. If you're moving backwards, your velocity is negative. If you're standing still, your velocity is zero. And similar idea with acceleration. If your acceleration is positive, you're speeding up. And if your acceleration is negative, you are slowing down. If your acceleration is zero, then you are moving at a constant speed. So here's a example. Let's say that we have a person. Let's do a diving board. So they climb up the ladder, and then here's the diving board, and you got a person up here doing a power pose, and they jump like this, and then they splash in the water down below like that. We could model the position of this person with a function, and I'll use um, pretty realistic numbers. So their position could be modeled as negative 4.9 t squared plus, I don't know. Let's say they can jump up at 9.8 t, and then that they're on a 10-meter high platform. So if I plugged in 0 to this function, that would tell me their position at time 0. If I plugged in 1, that would tell me their position at time 1. I'm going to mention here that the t is the time in seconds and the p is the height in meters. And I used these numbers here because they come from the speed that you fall, the acceleration of gravity. So the position tells me how high the person is at any time. The derivative of that, negative 9.8t plus 9.8, that tells me the velocity of the person at any time. So it tells me how quickly they're moving and in what direction. So if the derivative is positive, they're going up, and if the derivative is negative, they're going down. So a really natural question is to figure out when does your derivative equal 0. So if you set this equal to 0 and add 9.8t to both sides, and then divide by 9.8, I chose these numbers to work out really nicely. In general, you'll probably get some nasty decimals when you're doing like a real world kinematics problem. But right here, I got t equals 1. And if I look at the first derivative, let me circle that again. If I look at the first derivative, it's negative when I plug in a number bigger than 1, and it's positive when I plug in a number that's smaller than 1. When I plug in 1, the derivative is equal to 0. So what does that mean? At exactly 1 second, the person is still. They're not moving up, they're not moving down. They're momentarily still at the top of their jump. If I plug in 1 second to the position equation, that will then tell me the highest point on their jump. P of 1 would just be negative 4.9 plus 9.8 plus 10, which ends up being 14.9. This person has mad hops because that is like almost a 5 meter tall jump. Maybe it's a really springy board. We'll pretend it's a super, super springy diving board, but that's still pretty high. When the t-value goes forward, they start to fall down like you would expect. And you can see that in the derivative that over the course of time, their derivative gets more and more negative because they're falling faster and faster and faster. Last thing I'll do on this example is just take the second derivative. If I take the second derivative, I get negative 9.8, which is measured, which measures the concavity here, the acceleration. You can see that this is always a concave down shape to it. This is the acceleration due to gravity, so we're just ignoring wind resistance there. It's always a negative value because there's no point when they like scoop back up or anything like that. There's one other thing I was going to say. Yes, units. So P of t was measured in, all of this was measured in meters. Then when you take the derivative with respect to time, remember you can write that as this, dp over dt. So you take your measurement of meters and you divide by your measurements of time, seconds. So your p measurement over your t measurement, meters per second. And if you take the second derivative, that would be like d squared p over dt squared. Then you have meters per second squared, or some people like to write meters per second per second. Those are the same idea right there. So it's nice to double check that your units also make sense with your derivative equations. So I'll put up another kinematics video doing a couple examples from the problem set, but this is the big idea of kinematics. Please comment if anything is confusing.